Hello everyone, welcome to another Vulkan stream. Today we're gonna cover frame buffers, and since it seems like it's a short chapter, maybe we will follow with command buffers. And maybe even we will get to rendering some triangle. So let's see where we're at. We are running, but the window just pops out and quits. That is expected result. But let's go into the code. So last time we created the graphics pipeline with a bunch of state from the fixed pipeline, the shaders. So now that we finally are using all of these data structures, it's time to clean up. I'm gonna remove the underscore from all of these variables that weren't used before. So here, shader stages, the vertex input assembly, viewport state, rasterizer, multi-sampling, dynamic state. I think we are still not using, so I will leave the underscore. Underpass. And now here we have to replace all of these underscores. That should be it. Let's double check that it still compiles. We missed the rasterizer here. So now we should be good to go. Nice. So we're gonna start today creating the frame buffers. We have been talking about them on the past few chapters. We already specified the attachments when we were creating the render pass. The frame buffer object references all of the BK image views that represent the attachment. In our case, that will be only a single one, the color attachment. However, the image that we have to use for the attachment depends on which image the swap chain returns when we retrieve one for presentation. That means that we have to create a frame buffer for all of the image in the swap chain and use the one that corresponds to the retrieved image at runtime. Okay, so we are gonna need not one frame buffer, but as many as we have image views, it looks like. Okay, so let's create frame buffers as an array of they are represented by a handle, so initially they will be null pointers. And for the size, we can use the same as image, swap chain, images or image views. Should be the same. Like this. We're getting complaint. Yeah, because Rust cannot infer the type of the pointer yet, but we will continue. Next, here it's iterating for every swap chain image view, and then creating the frame buffers. So, all right. We can do the same. here we need to call this function to create the frame buffer. So it requires the device, then we need to pass the creation info, with all the parameters required. And after the creation info, we pass in null pointer and a reference to the frame buffers. We don't have an index, but we can let's do a for loop using for now. Let's do exactly what they are doing. So we have this index to use, and this will not yet compile because we need to add this function to our bindings. So let's go ahead and do it. So vk create frame buffer returns a result, and it takes the device. Let's find the function in the Vulkan header. So it takes the creation info, the callbacks, the allocator callbacks, and the frame buffer as an output pointer. I missed a comma, I think. After here should be a comma, right? Next, we can grab this frame buffer create info and add it to our list of structs. Hold on a second. I'm back. So I was saying that we need to add this definition for the frame buffer create info. So we can add it at the bottom of our struct definitions. It contains frame buffer create info, and if I look for it here, it has the following fields: the type of the structure, pointer to the pnext, some flags, the render pass, the attachment count, the actual attachments, which are image views, the width, the height, and the number of layers, I guess. So now we can grab all of these. Nah, that didn't work. Can grab all of these, go to our main, and paste them in here. We don't need the path. The S-type already have it. Now, for the pnext, we're gonna set it as null. The flags, it's gonna be 0 for now. Then we need to pass the render pass. The attachment count is gonna be 1. The attachments can be just a reference to this. Can I pass a reference to the swap chain image view directly? Swap chain image views at I. We'll see if that works. Then the width is gonna be surface caps extent. I don't remember. So when we create the swap chain, current extent, dot width, and the same for the height. We're gonna have just one layer, format it, and let's check if this compiles. Cannot find frame buffer create info in the scope. Is that so? Did I save? Frame buffer create info. So first we need to add the flags to our list. And now, do you like it? Frame buffer, create flags. Did I not name it BK frame buffer create info. I have dyslexia. Looks like. Now it checks out. Nice, good. So if we run it like this, without destroying it, probably we'll get some validation errors. So let's check that. And we do. Frame buffer, blah blah blah, has not been destroyed, but it should be destroyed. Okay. So let's head back to main. And on the cleanup, we can add for loop to destroy the frame buffers, basically. Passing the device, frame buffer, and null pointer. And of course, we need to add this to our bindings. I assume that the signature is something like this, but let's double check. Okay, destroy frame buffer, and I was correct. So if we run it now, we no longer get any error, which is nice. So let's check the changes that we did so far. And commit the changes. Push this. And let's take a look here. Yeah, the creation is quite straightforward. We just need to pass the render pass, the attachments, and the width and height. And the layer refers to the number of layers in image arrays. Our swap chain images are single images, so the number of layers is 1. And we should delete them. Alright, so before I continue, I wanted to do some changes. So because right now, basically I just create all the Vulkan objects and then proceed to destroy them. I want to add the main loop here, so because I had code for it in here, as you can see. I can get rid of this exit, and I can grab all of this and move it before I destroy everything, like this, and see if that still works. Not sure if I should destroy the display here or somewhere else, but we'll see about that. So now if I run this, I should get this, this window. You can see the window here, so we still don't render anything, but at least the application doesn't quit right after everything. So now if I press escape, the application quits. And we get a segmentation fault, it looks like. So basically somewhere our program crashed, and if I remember correctly, it is because we need to move this closing the display before destroying the Vulkan instance. Let's see if that fixes it. So we got the window, and if I close it, now we don't get a segmentation fault. So the reason for this is because the display from X11 and the Vulkan instance are somehow linked, and when we destroy the instance, basically the Vulkan library is completely unloaded, and since the display has a reference or some kind of link to the instance, we get these segmentation faults. Something like this, I seem to remember. So before yeah, something like this. And I can also commit these changes. Move the cleanup code after the main loop and push this. So now we can proceed to the next chapter, which is about command buffers. Commands in Vulkan, like drawing operations and memory transfers, are not executed directly using function calls. You have to record all of the operations you want to perform in command buffer objects. The advantage of this is that when we are ready to tell the Vulkan what we want to do, all of the commands are submitted together, and Vulkan can more efficiently process the commands since all of them are available together. In addition, this allows command recording to happen in multiple threads if so desired. Okay. Command pools. We have to create a command pool before we can create command buffers. Command pools manage the memory that is used to share the buffers, and command buffers are allocated from them. Add a new class member. So yeah, first we will have to create a command pool, and then we can allocate command buffers from this pool. So we will do that right after the create Framebuffers. So in here we're gonna have a command pool object initialized to null, and then I guess we're gonna have to call bk create command pool, which can fail, so we want to check for this failure, and we need to pass in the device, and as usual some creation information. So as you can see, Vulkan follows a very straightforward procedure for creating its objects, We always have a create function which takes the device, some struct specifying creation information, and we get the created object back as a pointer. Also, most of the structures have similar fields, especially the S-type. It's shared by almost all of the Vulkan structures. And a lot of them also have flags. And the pnext, which is used for adding extensions to the object we're creating it. But we mostly never use pnext, at least for now. So here we're gonna have to fill in more fields, but we also have the null, and we get back the command pool. So now we need to add this function to our bindings. And I like to always open side to side the The structure to create the command pool is pretty simple. It just has the S-time, the pnext, which we normally don't use, some flags, and the Q family index that we want this command pool to be linked to. Do they say something about this Q family? Command buffers are executed by submitting them on one of the device queues, like the graphics and presentation queues we retrieved. Each command pool can only allocate command buffers that are submitted on a single type of queue. We are going to record commands for drawing, which is why we've chosen the graphics queue family. Gotcha. So in our case, the graphics and presentation queue are shared. They are the same on this system. But it could be that on other systems they are different queues. So that's a special case that we need to guard against. So we need to add these flags as a type def. And here we were only missing Q family index, which in our case is gonna be graphics Q, graphics family index. Yeah. Let's see if we did get it right. Okay, we're just missing this flag value for command pool reset command buffer bit. So we can copy all of these flags. And I have here a bunch of constants that we already copied, and I will add them at the bottom. Now we just need to format them a little bit. Add const, word, dk flags. And just repeat. So now we should not have that error anymore, and we don't. So that's how we create the command pool, and I guess we're gonna have to destroy it on the cleanup. Yep. So we can add that cleanup code up here, down here. Destroy command pool for this device. And then add this. So now let's try to run it. And we are not getting any errors so far, and if we destroy it, we also don't get any validation warnings or errors, so we are good. Next, we need to allocate command buffers from this pool that we just created. So how do we do that? We will add a command buffer to the class, and then they are doing it on this create command buffer function, but we are doing everything in line in main for now. So let's see, we can have this command buffer, and then we just call allocate command buffers with a check, and we need to pass the device some structure to specify the allocation. this information, we need to specify the command pool we want to allocate buffers from, the level, which we are using primary. So we can have primary or secondary command buffers. The primary one can be directly submitted to queues for execution, but it cannot be called from other command buffers. And the secondary one cannot be submitted, but it can be called from primary buffers. We won't use secondary buffers for now, but they are used for using the recording of commands, I assume. So we are missing the command buffer count, which is just set to 1. And then, as usual, oh, we don't have allocation callbacks here, which makes sense because we are allocating from the pool. But we need the output command buffer object. And we need to add this method to our bindings. So it takes the device, and then we take the allocation information and we get the command buffers back as a pointer. And it can fail, so we return a BK result. Why is not formatting? I think I did something wrong. Yeah, I missed. No. So now we need to add the definition for this buffer allocate info, so we can go ahead and add it to the end. And it has the S type, the P next, command pool, the level for the command buffer, and finally the count of command buffers that we want to allocate. So from all of this, maybe this one we don't have it. And it's an enumeration. So we can grab this, oops. And port it over to our list of enums. we can export all of the variants so we don't need to namespace them using the type of the enum. Let's see. Missing pnext. Ah, right. We saw that this type doesn't actually. We didn't add a pnext. But does it have it? I don't remember now. Yeah, we have a pnext, so we can just set it to null. But we don't have flags. Okay, we managed to allocate command buffers. And do we need to deallocate them at the end? Okay, for now it doesn't say anything about deallocating them, so let's try to run this just to do a sanity check that we are still working fine. Okay, seems to be working. And move the window around, and if I quit I don't get any validations, so alright. I'm gonna commit this. So what are the changes? We create the command pool and we allocate, okay. Create command pool and allocate command buffers from it. Push. All right. So next we can already start taking a look at how do we record into the command buffer. So we'll start by creating a function that writes the commands we want to execute into a command buffer. Okay, we're not gonna create the function, but we are gonna directly call the things that they call inside the function. So where do they record the commands? They don't say. So I'm just gonna assume that we record before the main loop. We'll see. So we start And let's see in the header how this function signature looks like. It just takes the command buffer and this begin info. And it doesn't fail. So why are we checking for failure? No, it does return decay result. So it can fail. We need to define this structure. Which has just has the S type, pnex, which we didn't specify, class, and this inheritance info. We can add the flags as a type def. And we also need the inheritance information, which is up here. Let's see if that compiles. We are missing the pnext on main, so let's just add it. Anything else? Nothing else. So we just started to record the command buffer. So if the command buffer was already recorded once, then a call to begin command buffer will implicitly reset it. It's not possible to append command buffers to a buffer at a later time. Okay, so starting a render pass. Drawing starts by beginning the render pass with vk begin render pass. So can call begin render pass, takes the command buffer and the render pass info. And also this constant subpass contents inline. So we are gonna add this. To our list of functions. I'm gonna separate them by comments. And that takes the command buffer, the render pass begin information, and the last flag is called contents, and it's just this type bk subpass contents. So add definitions for this struct. Here it is. Let's type next. Render pass, frame buffer, the render area, the clear value count, and these clear values. From all of these types, I think we need to define this one, which is what exactly? It's a union. Do you have any other union? No. So this is gonna be our first union. Let's see if we can just use because Rust has unions, but they are not so used so often, I think. So let's see if that works out. So it can either have a bk clear color value or a depth stencil. And we're gonna have to define both of these. But they are structs, so up here. So the clear color value first has, no, it's a union as well. But the clear depth stencil is a structure. So let's do that one first. And it contains a depth value, which is a floating point, and the stencil value as an unsigned 32 bits. Okay. And then we need another union for the clear color. Which can either be float 32, so 4 F32 values, or it can be 4 int in 32, or it can be 4 unsigned integers. Okay. Do you like this compiler or not? Unions with non-copy fields other than manually drop are unstable. What if I derive copy for this and also for the depth stencil? Is it better now? I need to add clone as well for both of them. Unions may not contain fields that need dropping. What field contains dropping? So let's do a cargo check. Cannot find this. Depth stencil. I did a typo. So now we were getting another error about the subpass contents. So let's search that one. This is just an enum. So, oops. So we can add it at the bottom. And now we need to fill in all of this information. which was S-type. The pnex we don't care. Then we have the render pass, the frame buffer, which we are passing some kind of image index. Is this a parameter of the function? Yeah. So for now I will hard code it to 0, but later we will see where do we get it from. We need the render area, which is a bkrect2d, which itself has an offset, bk offset 2d, and also an extend. This one we can just get it from the surface caps current extend, if I'm not wrong. Finally, we're gonna have one clear value. Let me scroll this up. Clear value count is gonna be 1, and the p clear values is gonna be a reference. I'm not sure how's that gonna work. Clear color, where does this come? Ah, it's up here. bk clear value. Do we need to be explicit about the union? So do I need to specify color? Let me look for this. Rust union. So yeah, we need to specify which one of the fields. So yeah, we can use color and then bk clear color value, and then I guess float 32, and then just an array of all zeros except the alpha. Does this compile? Amazing, amazing, it compiles. Okay, so let's continue. Next, we can bind the graphics pipeline. But I'm gonna take a short break to turn up the lights and go to the bathroom. So see you in 5 minutes. Okay, I'm back. For some reason, I'm not receiving subscribe notifications, so sorry for that. I think Pedakin followed. Thank you so much for the follow, Pedakin. If you're still there, I'm sorry. But I'm still super new to streaming. Let me see if I can see why I was not getting notifications. Desktop audio. I will try to trigger Streamlabs follow notification. Yeah, so when I emulate the flow from stream elements, it seems to be working. But I don't know why I don't get the notification when a real follower happens. So I will need to look into this. I just don't know how to test this. But okay, let's continue with the recording of command buffers. So we did the begin render pass, and now the next step is to bind the pipeline. So we do that using this command, passing the command buffer. We want to bind to the graphics point, and we want to use the pipeline that we just created. So let's add to the list of our commands in the bindings. The second parameter is pipeline time point. And the last one is the pipeline itself. We are probably gonna have to add the pipeline bind point, don't we? Do we have it already? Yeah, we already have it from when we were creating the pipeline. Cool. So what's next? We bind the pipeline, and next we finally get to recording a drawing command. We specify the command buffer, the vertex count, that we specify it as 3. Even though we don't have a vertex buffer, we were hard-coding the vertices into the shader, the vertex shader. We're hard-coding here the positions and the colors. So, but we need to specify 3 vertices because we're using the GL vertex index. So yeah, we will need 3 vertex count, and then the instance count, which is used for instance rendering. We can use 1. Then the offset to the first vertex, which is gonna be 0, and the offset to the first instance, which is also 0. Okay, so seems simple enough. Command draw, command buffer, 3 vertices, 1 instance, and start from 0. And then add it to the list. It takes the command buffer, the vertex count, the instance count, first vertex, and first instance. Cool, cool, cool. Next we're gonna need command and render pass. I'm gonna add it here already. which just takes the command buffer. And we also need the end command buffer. Which takes the command buffer. And can fail, so PK result. Let's double check the signature for these two. Okay, this one seems okay, and command buffer seems okay to me. So now we just need to call them from main. Command and render pass. And the command buffer. And we can add in the check macro. I missed the FN keyword for this one. Let's try to run this. So I think we still won't see anything because we are recording. Yeah, we are recording the commands, but we are not using them in any way. So we don't get any error, but we still don't see anything on our screen. So I guess that we'll have to wait until next chapter. So let's see, what did we do? Record the commands. Let's commit the changes. And push it. So let's go for the next one and see if we can finally get a triangle on the screen. It's taking a while. This is the chapter where everything is going to come together. We're going to write the drawFrame function that will be called from the main loop to put the triangle on the screen. Let's start by creating the function and call it from main loop. So basically, in our case, we have all this code for processing events, and then right after this while loop, here we can draw, basically. We'll see how, but outline of a frame. At a high level, rendering a frame in Vulkan consists of a common set of steps. Wait for the previous frame to finish, acquire an image from the swap chain, record a command buffer which throws the scene, submit the recorded command buffer, and present the swap chain image. So we will expand this on later chapters, but for now this is the basic skeleton. Synchronization. So we're gonna need synchronization primitives. Really? The order of operations It's up to us to define using various synchronization primitives, which tells the driver the order we want things to run in. This means that many Vulkan APIs calls which start executing are asynchronous. In this chapter, there are a number of events that we need to explicitly order because they happen on the GPU. For example, acquire an image from the swap chain, execute commands that draw, and present the image to the screen. Each of these events is set in motion using a single function call, but all of them are executed asynchronously. The function calls will return before the operation actually finishes, blah blah blah. This is unfortunate because each of the operations depends on the previous one finishing. Thus, we need to explore which primitives we can use to achieve the desired ordering. Semaphores. Semaphore is used to add order between queue operations. There are two kinds of semaphores in Vulkan, binary and timeline. And we're only gonna use the binary ones, okay. Semaphore is either unsignaled or signaled. It begins as unsignaled, and the way it works the same semaphore is used by signaling in one operation and as a wait semaphore in another queue operation. So if we have semaphore S and queue operation A and B that we want to execute in order, what we tell Vulkan is that the operation A will signal semaphore S when it finishes executing, and operation B will wait on semaphore S before it begins executing. Okay. When operation A finishes, semaphore S will be signaled, while operation B won't start until S is signaled. After operation B begins executing, semaphore S is automatically reset back to being unsignaled, allowing it to be used again. Okay. So semaphores can be used to synchronize between two queue operations, basically. And will the semaphore block the current thread here it says. Yeah, of course. So yeah, my question is BK queue submit blocks or not? No, in this code, both calls to queue submit return immediately. The waiting only happens on the GPU. The CPU continues running without blocking. To make the CPU wait, we need a different synchronization primitive, which we will now describe. Okay, so semaphores do not block, well, at least not on the CPU, and fences, I guess. Fences have a similar purpose, that is to synchronize execution, but it is for ordering the execution on the CPU or the host. Simply put, if the host needs to know when the GPU has finished something, we use a fence. Okay. Similar to semaphores, fences are either in signaled or unsignaled state. Whenever we submit work to execute, we can attach a fence to that work. When the work is finished, the fence will be signaled. Then we can make the host wait for the fence to be signaled, guaranteeing that the work has finished before the host continues. I see. A concrete example is taking a screenshot. Say we have already done the necessary work on the GPU. Now we need to transfer the image from the GPU over to the host and then save the memory to a file. We have a command buffer A which executes the transfer and fence F. We submit command buffer A with fence F. Then immediately tell the host to wait for F to signal. This causes the host to block until command buffer A finishes execution. Thus, we are safe to let the host save the file to disk as the memory transfer has completed. So we have a command buffer A and a fence F. We submit some work to the queue specifying the fence, and then we wait on the fence. And this is gonna block the current thread, so in the CPU, until the operation A finishes. And after that, we can save to disk, okay? Unlike the semaphore example, this example does block the host, yeah? In general, it's preferable not to block unless necessary. So that's why we prefer semaphores or other synchronization not yet covered. Fences must be reset manually to put them back into the unsignaled state. This is because fences are used to control the execution of the host, and so the host gets to decide when to reset. However, semaphores are automatically reset. In summary, what to choose? You have two synchronization primitives to use and conveniently two places to apply synchronization: swap chain operations and waiting for the previous frame to finish. We want to use semaphores for swap chain operations because they happen on the GPU. Thus, we don't want to make the host wait around if we can help it. For waiting on the previous frame to finish, we want to use fences for the opposite reason, because we need the host to wait. This is so we don't draw more than one frame at a time, because we re-record the command buffer every frame. We cannot record the next frame's work to the command buffer until the current frame has finished executing. Okay, so here they finally say that we're gonna record every frame, but we did it just one time before the main loop. And we were hardcoding the image index. So yeah, probably we're gonna have to deal with this. We cannot record the next frame's work to the command buffer until the current frame has finished executing, as we don't want to override the current contents of the command buffer while the GPU is using it. So we're gonna have to create some synchronization objects. I'm gonna do it right before recording the commands, actually. And what do we need? We need two semaphores and one fence. And we start with the semaphore. So we can reuse the semaphore info, looks like. And the two semaphores, we're gonna name them image available semaphore. And the second one, render finished semaphore. Then we have the semaphore create info. And then we just pass the device, semaphore create info, null pointer for the allocation callbacks, and image available semaphore, and exactly the same for the render finished semaphore. And now we just need to fill in the creation structure. So the S type, semaphore create info, and it looks like everything else we set by default, but doesn't say which are the fields, so we will need to look it up on the Vulkan header. So yeah, the device, the second parameter is the creation info. And the allocator. And finally we get back the semaphore object. We will need to put this somewhere. Maybe before all of this command pool, command buffer, yeah, before the render pass begin. So we just have the pnext and flags. So here pnext is gonna be null, and the flags we don't use any as far as I know. Expected. So did I not set the proper return type? I forgot to return a decay result. And after create semaphore, we can also add the signature for the destroy, and I'm gonna also add the ones for create fence. And also the other functions related to fences, the wait and reset. Okay. So let's fill in all of these functions. So destroy semaphore takes in the device, the semaphore, and the allocator. They create fence, takes in the device, creation info, the allocator, and gives back the fence. Destroy fence, it's gonna take very similar things, I assume. And this one probably, yeah, returns a decay result. So device, fence, and allocator. What the fuck are you doing? Wait for fences. Reset for fences. Wait for fences. Takes in the device, the fence count, a pointer to fences. So we can wait on multiple ones. And then we have a wait all flag and a timeout. And this can fail. I assume if we don't make it in the timeout, maybe. Then reset fences takes the device, fence count, and the fences. So from all of these, I think we need to add in the definition for the fence grid. So let's add it after the semaphore. And it's exactly the same as for the semaphore. We just need the be next and the flags. Except that the flags are different. So now we can create the fence as well. DK create fence, device. This time, since we're only creating one, I'm gonna put the creation info inline. So we just need the S type. Next, and flags are empty. Then no allocation callbacks. We store the results in this variable which we need to create. Let's see that we didn't miss anything. Mismatch, closing the limiter on line 616. 616. That's right, forgot one closing parenthesis. And now we should be able to run this and get validation errors. When we close the window, it complains that we are not cleaning up the two semaphores and the fence. Yeah. So we need to add the cleanup code. So BK destroy. I'm gonna reorder them. Last in is first out, like on a stack. So destroy fence, in flight fence, no pointer, and also BK destroy semaphore, device, render finished semaphore, and the same for image available semaphore. Now I expect not to get validation errors, and we don't. Let's commit this. What's next? Waiting for the previous frame. So on our main loop, here on the draw, the first thing we need to do is wait on the fence. Device 1, in flight fence, BK true, and U64 max. Do we have it in Rust like this? And this could fail, so better check for it. Right? But takes an array of fences and waits on the host for either. So here we are blocking. We want to wait for all the fences, but we only have one. After waiting, we need to manually reset the fence to the unsignaled state with PK reset fences. So after this, PK reset fences takes the device, one in-flight fence. Does this fail also? PK reset fence. This one also can fail. So check for this. What don't you like? It just failed. Okay, before we can proceed, there is a slight hiccup in our design. On the first frame we call draw frame, which immediately waits on in-flight fence to be signaled. In-flight fence is only signaled after a frame has finished rendering yet since this is the first frame, there are no previous frames in which no signal to fence. Thus, wait for fences blocks indefinitely waiting on something which will never happen. Of the many solutions to this dilemma, there is a clever workaround built into the API. Create the fence into the signal state so that the first call returns immediately since the fence is already signaled. To do this, we add the fence signal bit flag to the create fence. Okay, I just want to run this and check if it really blocks the thread. So how do we know that it's blocking? Oh yeah, it blocked because it didn't quit properly. So if I do a print line here, it doesn't print it, and even if I cannot quit the application, and if I force quit it, I still don't see it. I need to Control C out of it. So it is blocking. Yeah, it is blocking, definitely. So the way to fix it is by creating the fence with this flag. So here, Dishin, thank you for the follow, man. How are you doing? So we can add this flag in here, but I don't think we have it defined on our bindings. So let me search for it and copy these two values. And go to BK. And here at the bottom we can add them. Here. We are starting to get a bunch of flags. Public PK flags. No, it doesn't format because I forgot the const. Like that. So now we are getting the fence initially signal. So if I run it now, we should be able to see the. In fact, let me add back the print line here after the reset. So we should see a lot of spam showing that print line message. Well, we only get it once because then we reset the fence to one signal and we never signal it again ever. So we will see this once. Okay, what do we do next? Acquiring an image from the swap chain. The next thing we need to do in the drawFrame function is acquire an image from the swap chain. Recall that the swap chain is an extension feature, so we must use a function with the bk khr naming convention. So yeah, gonna delete this, then declare an image index variable which we can initialize to 0, and then we can call this function passing the device, the swap chain, use 64 max, the image available semaphore, bk null handle, and store the image index that we get back in this variable. Like this. The first two parameters are the logical device and the swap chain. The third specifies a timeout. So we don't want any timeout, so we specify the maximum possible unsigned integer. And the next two parameters specify synchronization objects that are to be signaled when the presentation engine is finished. That's the point in time where we can start drawing to it. It is possible to specify a semaphore, fence, or both. We're gonna use the image available semaphore for that purpose here. The last parameter specifies a variable to output the index of the swap chain image that has become available. We're gonna use that index to pick the bk frame buffer. And then we can start recording. Okay, so let's add this function to our bindings. Where do I want to add it? Because maybe I want to put it close to the other swap chain khr get swap chain images, maybe here. bk acquire, have it here copied. Text the device, swap chain, timeout, a semaphore that we can signal, and a fence, which we don't need in our case, but we could use it. And it gives back an image index as a pointer. And it can fail actually. So let's add the check macro. Since this can fail, I don't want to go with errors unnoticed. We don't have a null handle, but we can just pass in null pointer. Should be the same. Okay, it compiles. With the image index specifying the swap chain index, swap chain in image to use in hand, we can now record the command buffer. First, we call reset command buffer on the command buffer to make sure it is able to be recorded. I thought that the command buffer was reset every time that you begin recording into it. But maybe I was wrong. So here, in theory, we need to call bk reset command buffer, passing in the command buffer and 0. And we can add this to the list. I'm gonna add it after bk and command buffer. Takes in the command buffer and what else does it take? Some flags. Okay, command buffer reset flags and returns bk result. So we just need to add this flag type def. And since we are not using it, we should be fine. Now it's the point where we record the command buffer. Here it says to call the function, but I have the code up here, not in a function yet. So let me grab it. Up until here and paste it down there. And the image index, we were hardcoding it to 0, but now we get it from the bk acquire next image, so I can get rid of this thing, format this, and we are just recording everything in line. Are we still good? Slice indices are of type usize. Okay, so 686. This needs to be a usize. Now we're good. With a fully recorded command buffer, we can now submit it. Key submission and synchronization is configured through parameters in the bk submit structure. So we need to call this bk submit. That's That's the gist of it. So submit one buffer. And we are submitting to the graphics queue. And we have one submit information structure. Okay, submit info. And we want to signal the in-flight fence, right? We add in some check. And now it's time to add this to the bindings. Where are we using the queue? Get device queue. And queue submit. There are a few variations of this function, so we want this one. Text the queue, the submit count, the submits structure. Well, it can be an array, but you can see it is represented as a pointer. And a fence that we can signal. And returns a result. Do we need any other function? I don't think so. And this is not psubmits, but bk submit info, which I don't think we have some anywhere. So let's add it. Not here, but no, actually, yeah, here. And let's see what it has. This one. So it has, as usual, the type, the pnext, the wait semaphore count, the semaphores, some mask, p-wait destination stage mask, const vk pipeline stage flags, command buffer count, command buffers, semaphore count. Need to go quickly to check something. I'll be back in a minute. Sorry for that, I'm back. So we were finishing the submit info struct. Signal semaphore count U32, and finally this signal semaphores PK semaphore. So in our main now we can fill in this submit information. So the S type is submit info. Then pnext can be null. Wait semaphore count is gonna be 1. Wait semaphores. We want the image available semaphore. We don't need to create this temporary array to just fill it with one. If we wanted more semaphores, then this makes sense, but if we're just gonna specify one, why not pass in the pointer directly? It should be safe. And the wait stages, the wait best stage mask, wait stages. This is also a pointer, right? So this one I'm not sure if it's gonna work because it's a value. It should work also. Maybe I will need to add constants for it, but it should work. Then command buffer count, we have only one. The p command buffer is a pointer to the command buffer. Here, why don't they? This should be a pointer. I don't understand why. Well, let's see if it works. Then signal semaphore count is gonna be 1, and the signal semaphore is the render finished as a pointer also. So this one looks like we don't have it. So search for it. and we have a bunch of them. So we can copy them here. And there are quite a bit of them, so I'm gonna try to record Beam macro. Start recording, insert, tab, const, word, end to the word, append, pk flags to the end of the word and replace with a semicolon. Then go to the next row, to the beginning, and quit. Now, did the macro work? Looks like yes. So repeat a few times. I think there's something wrong here. Looks correct to me. Does it compile now? It does. Surprisingly. So we are submitting then. Is it going to work now? Now on the next frame, the CPU will wait for this command buffer to finish before it records new commands into it. We have this section about subpass dependencies. Let's try to run this now. We are not waiting on some semaphore, so still doesn't work. So subpass dependencies. So, and this is on the render pass. Subpass dependencies. So we need to add one dependency here. I'm just gonna do it as fast as possible without reading too much. So the source subpass is external. The destination subpass 0. Source stage mask is this thing. Destination stage mask is this thing. And the source access mask is 0. And the dest access mask is color attachment right bit. And dependency flags, we don't have any. Check this. Okay, we need VK subpass external. Which is VK subpass external is all ones. It's just a U32. So I will add it down here. Popcons, VK, subpass, external. U32 is not 0. Not sure if that's bitwise not. I'm gonna assume it is. Then we get PK access, color attachment, right bit. Only that error? Almost there. So PK access flag bits, copy all of these. Then go here to pubconst, put it at the bottom. Record the macro again. Oh, we should have the previous macro. Should have worked. Pub, const, word, and append, bk flags, end of the word, replace, go back, go to the beginning, and repeat a few times. What is going on? Where was I? Here. Do I still have the macro? I do. 11 more times. Cargo check. Compiles. Finally, we need q%. Submit. It takes the percent %q, but in our case it's the same as the graphics queue. We check that it supports both. And bk percent info kchar. And filling everything. This is a KHR extension, but I don't care. So this one returns a decay result. Now we just need to define this struct. Next, wait semaphore count, wait semaphores, swap chain count, swap chains, image indices, and we get back results as a mutable array of result. So we need next, it's gonna be null. Wait semaphore count, it's gonna be 1. The actual semaphore is gonna be signal semaphore. Render finished. Semaphore. Where else? Where else? Swap chain count is gonna be 1. our swap chain, image indices is gonna be our image index, and the p results, we don't care. I think it's the moment of truth. The moment of truth. Please make it work. Whoa! Look at this. Oh, it crashed. Because we resized the window. But look at this. It's our triangle. Oh my god. We got it. So if I quit, we get a bunch of validation errors. Because we are trying to destroy fences and semaphores before they are finished being used. So we can add this to quickly fix it. So right after our main loop, just wait on the device, and let's add this function. Before the commands, just takes the device, and I'm not sure if it returns an error. Yeah, so it returns a decay result. So I will add a check, and hopefully now we don't get any errors when we exit. We get our triangle, we exit, and look at this, clean exit. Exit code 0, great. So I will commit the changes, and I have to go already. I streamed for 2 hours and a half. Longest stream so far. So what I'm gonna mention in the comment, rendering ampersand, acquire image, render ampersand. Acquire image, render ampersand. Push it right into the repo, and that would be all. If you want to check out the source code, you can check it out on my GitHub repository. It's in here. I will share the link in the chat. And yeah, that was all for today. Thank you all for watching. I will see you next time. Bye.